We left off last class looking at a wave generator, and I showed you guys a particular instance where the wave was standing, meaning that the wave coming in reflected and interfered with the wave that was going this way, and we saw something that looked like it was standing in space. For this video, I'm just going to consider the string, or in this case, a spring. It's going to work for my visual representations because it's a little bit bigger, so the wave speed is smaller. We need to understand that to get a standing wave in a string, we need to fix both ends. So let's say that this is a wall, and this is all fixed in so it can't move up or down, and we can just say that someone's hand is oscillating this on the other end. From this picture, we can define some things. We can call this a node, and this would be the antinode. And this should be also a node. So the nodes are not moving in space as time progresses because the wave coming in this way will interfere with the wave going that way, and it's completely destructive, so this node will just stay in space. Whereas the antinode, well, it's going to oscillate between both of the amplitudes at the bottom and the top. So you could pick them out here. Here I've got my node, 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 and my antinode right there. Antinode, antinode, antinode. The frequencies that are oscillating the spring or string, these are going to be called resonant frequencies if we do indeed see a standing wave. So for this first case, this is a standing wave, and it's the most basic standing wave that we can see. We call it the fundamental frequency. So it's our first resonant frequency. Then we could oscillate it at a bit of a faster rate, a higher frequency. Let's see if I can do this here. So something like that, where we get a full standing wave. Oh, I'm losing it because it's rotating as well. But you get the picture. That we could get this scenario to play out if we fix both of our ends, and I'd have to rotate, or I'd have to oscillate this at a higher frequency. And it follows that with every step down, or if you see more waves in this fixed string, I'd have to oscillate it at an even larger frequency. All of these are resonant frequencies, but this one here is our fundamental frequency because we can't, this would be the very minimum frequency in order to get a standing wave. So let's look at actually solving out and determining these fundamental frequencies, or resonant frequencies. Okay. I'm going to assume that the length of the string is L, and in this first case, my standing wave is a half wavelength. So if my full wavelength, I'm going to use a different color, a full wavelength is getting back to the original spot or original position in the wave, so my full wavelength would be something like that. I only see half of that, and that makes up the entire length of the string. So I set those equal to each other, and I want to come up with an expression for the wavelength. So the wavelength of this standing wave is 2L. The reason why I want to write a few expressions for my wavelength is because I'd like to write out an expression for the frequency. And I know that the wavelength and the frequency are related by the velocity. So I rearranged that for the velocity, and I came up with this. And I want to try and make an expression for the wavelength for standing waves. So here I go with the next possible standing wave. In this case, I see a full wave. So wavelength is one wavelength. The length is still L. So my expression for wavelength is L. The next one down, here I see, well, I've got one wave and then a half wave. So 1.5 wavelengths or 3 over 2 wavelengths. Solving that for lambda, I get 2L over 3. What's the pattern here? Well, I start with 2L, and I think you're dividing by some number, and that number is increasing with every bit of half wavelength that you have. So here, my pattern I'm saying is I've got lambda, and I start with 2L. Here I divide 2L by 1. Here I divide 2L by 2. Here I divide 2L by 3. So this n is just going up by 1 every single time I increase my frequency to get to a standing wave. So the frequency of resonance for my string here is V over lambda, but I have my expression for lambda, and I get this. My frequency to oscillate a string is dependent on the velocity of a wave and the length of a wave, or the length of the string. So let's look at this here. I've got this long spring, and I've also got this shorter one. So this expression is telling me that it should be easier to get an oscillating standing wave for the longer spring than for the shorter spring. And that's indeed what I find. Even though I can get this fundamental frequency, it's really hard to get the following standing wave. I don't even think I can do it. It's also telling me, if I recall, that velocity is the square root of tension over mass density, that if my mass density goes up, the speed goes down. If the speed goes down, then my fundamental or my resonant frequencies is lower, meaning it's easier to get a standing wave on a spring, which has a higher mass density, than a little strand of string, which has a very low mass density. And just know that this n, it could be any integer. The higher the integer, the more wavelengths we have in our standing wave. All right, that's it for now. See you soon.